Okay, guys, today we are going to talk about cell transport. We're going to talk about how stuff moves into and out of the cell.
I'll do it myself. I promise. I meant to, but then I forgot to talk about package.
Okay, so there are two general types of transport in and out of a cell. There is what we call passive transport and active transport. Passive transport means that it doesn't require any energy. So when we need to move something into the cell, it doesn't require any energy to get it into the cell. So for an example for you, this is my cell membrane, okay? See, there's holes in your cell membrane. You know how stuff can move in and out of your cell membrane? Okay, we have holes in our cell membrane. This is my cell membrane. My jug is going to be our cell, okay? So in passive transport, stuff just goes right through the cell membrane. Bigger things are kept out. They can't pass through the cell membrane. Smaller things, oh no, run away, just pass straight through. That is passive transport. Okay? There are three types of passive transport: diffusion, facilitated diffusion, and osmosis. Thank you. You guys got this one?
Ow. I am.
Okay. So diffusion, I don't have to do anything with. Diffusion is the movement of particles from an area of high concentration to an area with lower concentrations. So just a normal container of water, okay? Regular food coloring. Okay? I'm not going to do anything to this. I'm not going to stir it. You can literally see those particles moving, right? That's diffusion. Okay? Where I first put that drop, okay, ready? Watch. Where I first put the drop, that's an area of high concentration, right? Because that's where the dye is. The clear water is an area of low concentration. Now I will leave this set, and as we leave this set, what we're going to see is it is going to even all out, and it'll eventually all become one consistent color of purple without me stirring or doing anything.
I can hear you, I promise.
I don't care. Put it away. It's rude.
I didn't mean it. I apologize. Don't accept my apology?
I accept your apology. Okay, so diffusion is controlled by temperature, it's controlled by pressure and concentration. So the water that I have there is from out in the bottle filler, so it's a little cold. If I use hot water, it might take and it might happen faster. Now, what I'm going to do through the course of the day is I'm going to leave this one here set, and I'm going to use this one for demonstrations for the rest of the day, because I'm going to leave this one set, and it's going to reach dynamic equilibrium. And dynamic equilibrium is where all of these particles will be evenly distributed throughout this beaker. So what's going to happen is it will be all one consistent color. If you look at it now, you can see that the particles are still moving. Have I had to do anything to this beaker? No, I didn't have to stir it. I didn't have to move it. It simply is moving the particles around on its own, and eventually it will equal and it'll reach dynamic equilibrium. Again, if I put more drops of food coloring in there, it's going to affect how long that happens. If I change the temperature, maybe the water was warmer, those particles will typically move faster. Warmer particles move faster. So we could reach dynamic equilibrium faster. So each one of these, I have a real life example for you. So diffusion in real life. When you look at your lungs, okay, you take a deep breath in, it goes down through your trachea, it goes down into your bronchioles, and at the end, you have these little tiny sacs. They're called alveoli. They are what comes in contact with where your blood is. That's how your oxygen that you breathe in through your lungs actually gets into your bloodstream. That deep breath in, it goes in, it fills up those little sacs with the oxygen, and those little sacs, they come in contact with the blood. The oxygen particles are exchanged into the blood. This also occurs in photosynthesis. We have a gas exchange between, the plant taking in carbon dioxide. This is also how the oxygen from your blood moves into your tissues, like your muscle tissues, your heart tissues, all of that. And another example of diffusion is what we call osmosis, and it's a special type of diffusion, and it is the movement of water across a semi-permeable membrane. Next, we have what is called facilitated diffusion. So if you look at my cell model up here on the board for you, I can turn that and you guys can see the board. So if we look at my cell model here, regular diffusion are these little particles moving back and forth in here. So you've got your little marbles and they just go back and forth across the cell membrane. Facilitated diffusion is using these little protein channels to move back and forth. Because they're small enough to slip through, they don't require any energy. I made sure Zoe's not in the shot. Everybody can hear you talking about that. So during facilitated diffusion, our real life example would be getting glucose into the cell. So glucose is a little bit bigger molecule. It's a little bit too big to slip directly across that phospholipid bilayer. So it uses the tunnel. And the tunnel is those proteins that we have embedded in the cell membrane. type of passive transport that we have is osmosis. And osmosis is a special type of diffusion, and it's the diffusion of water across the selectively permeable membrane. Now, the amount of water that we have moving into or out of a cell is called osmotic pressure. There are three types of concentrations that we need to talk about with that osmotic pressure. And they are isotonic, hypotonic, and hypertonic.
That's what I'm trying to do.
Well, but the important thing to look at there is the first part of the root word. Iso, hypo, and hyper. Remember what I told you guys at the beginning of the year. And I know we've kind of got away from our root words because it's a little bit hard to do it with everybody being so split up. But if you can figure out what parts of words mean, it often helps you to figure out what an unknown word is. Osmotic.
Conjuga. I forgot where I even was.
O-S-M-O-T-I-C. Osmotic.
M-O-S-O? Oh. I'm lost. M-O-S-O?
It's right there. O-S-M-O.
O-S-M-O.
T-I-C. Terminology. So let's talk about isotonic. So in an isotonic cell, what we see is that this is a normal cell state. So when we look at this, the cell looks normal. This is a normal red blood cell. A normal red blood cell looks like you took a Play-Doh ball and pinched it and smushed it in the middle. Or like those thumbprint cookies. You know the thumbprint cookies? That's kind of what a normal, huh?
They're salty.
No. They're the ones that like are typically, they're like a dough. Well, those are the Kiss cookies. I'm talking about the ones they normally fill with icing. But it's like you take a ball, you round ball, and you press it in the middle. That's what a normal red blood cell looks like. This is what a normal plant cell looks like. And this is a diagram. And you see when they show you, the water is moving into and out of the cell at the same rate. The arrows are the same size. This is isotonic. You're taking water into the cell and losing water out of the cell at the exact same rate. Hypotonic. Does those cells look like those normal cells we just saw? The answer would be no. Look at that red blood cell. That red blood cell looks big and swollen. You are taking more water into the cell than is leaving the cell. So if you look at that first one, that first diagram, you see the arrow for the water going into the cell is bigger than the one that is leaving the cell. And if you look at even the plant cell here, I'm going to take that from. If you look at the plant cell here, your central vacuole looks all swollen and big. And if you look here, even see how it's bulging out around. Real life examples. Somebody who has congestive heart failure, they retain water. Somebody who has to go on dialysis. This is like what their blood cells and that would look like. They're holding on to too much water. They're not getting rid of enough water for their cells to function normally. Hypertonic means that they're losing too much water. And if you look at that plant cell, that literally, your central vacuole has literally shrunken up and it has pulled away from the sides of the cell wall. Now look at that blood cell. Tell me when you think a blood cell would look like that. When somebody's what? When somebody gets what? Too much water is leaving the cell versus entering the cell. Dehydration. There you go. That's exactly right. When someone is dehydrated, that's what the cell will look like. You guys good? Okay. So next we have active transport. Active transport requires energy. Passive transport. They just pass right through. Active transport, my molecules do not go through. It requires energy to get them through. I can get them into my cell, but it requires work. I have to actually do work and apply energy to them in order for them to get into the cell. Okay. So real life examples of active transport, the most important one would be your heart. So every time your heart contracts, this is what happens. It's called the sodium-potassium pump. This is actually what happens every time the muscle contracts. Well, when we talk about your heart's a muscle, and every time your heart beats, that's a contraction. So what happens is sodium and potassium move into and out of the cells in order for them to contract. This requires energy because those are bigger molecules. Another example of this would be your glucose being taken into the intestine to be able to use for energy. Or this would be in plants where they're pulling the nutrients and the minerals out of the soil through their roots. It requires energy. It is active transport. It doesn't just slip through those cell membranes like we saw with passive transport. And if you look at that beaker up there, you should notice that beaker up there. What do you notice about our beaker? So what's the right term? It has reached what? What was that word? It was actually two words. It's almost there. There's still a few little streaks, but you can clearly see that this is starting to reach what? Got it, Zoe? Perfect. Dynamic equilibrium. Okay? And did I do anything to this beaker? Have I come over? Have I stirred it? Have I shaken it? Have I done anything with it? The water molecules are moving. Molecules are always moving. So, like your atoms are always in motion. I don't have to do anything because those are moving around in there. That's exactly what happens in your body. And it doesn't require any energy. One more that does require energy is how we get big things in and out of cells. These are like really large particles, how we get them into and out of the cell. And what they would take and do is, if you look at your cell membrane, they're going to push and push and push on this cell membrane until it encapsulates it and it gets rid of it. And you can see that on the slide there. So if you guys ever had a splinter and you didn't realize you had a splinter, you know, like it was a small splinter and you didn't know you had it till like a day or so later when it started to like get all red and swollen up. That is an example of exocytosis. It's actually trying to push out that splinter. So what happens is all of these white blood cells rush in, they encapsulate that splinter because it's a foreign body in your body, and it's trying to get rid of it and push it out. So it completely encapsulates it and pushes it and pushes it and pushes it until it actually pushes it out of the skin. Now, the opposite of exocytosis would be endocytosis. Endocytosis is how we would get really big things into our cell. And what happens is the opposite, is it pushes into the cell membrane until it encapsulates it. And it walls it off and takes it into the cell. Okay? That is the end of section 3 notes. We are almost done with this. We'll finish up the notes in that next week. We're going to wrap up our cell stuff next week. Okay? So our chapter with cell stuff is all going to be done. Well, I guess we're not completely done with cell stuff because we need to learn about how cells divide and that. But we're done learning about the parts and pieces of cells. And next we're going to move into like how they get their energy, cell division, and genetics. So, questions? Does it relate to what we're talking about?
Yes.
What's your question?
How much time do I have on this project?
Monday. Your project's due Monday.
You gonna help me with it?
Pretty sure I've already helped you with